Okay, chapter 9 brings us to the final chapter in the textbook. Hopefully we'll get to a good chunk of this. It describes and talks about the relationship between points and lines and planes in 3 space. And really, it's about solving systems of equations. And so there's going to be a lot of algebraic work and working with equations in order to find out where lines intersect or how they interact with each other in 3 space, how a plane and a line interacts or intersects with each other, and 2 planes intersecting with each other, and 3 planes intersecting with each other. So a lot of geometric uh, algebraic work and understanding what the systems look like, and working with the equations in order to solve for these particular situations. So there's the explanation, the intro to chapter 9. The okay, the next slide, as we've been doing, talk about learning goals. So we're going to understand the relationship between the intersection of a line and a plane, and between 2 lines in 3 space, algebraically solving systems, understanding the intersection of 2 and 3 planes, and then calculating distance from a point to a line and distance from a point to a plane, and calculating distance problems relating to lines and planes in 3 space, and interpreting these results. And following the learning goals are success criteria, just builds on each of those learning goals, that we can solve a system of equations, understanding if it's how lines interact and intersect with each other, and planes, and then solving some distance problems as well here. So we're going to set the stage here and criteria for a couple of things here. First of all, we're going to talk about the intersection of 2 lines. Section 9.1 is actually a pretty big section here, so I'm going to break it into 2 videos. First up is the intersection of 2 lines, and all of this work is done in 3 space. Okay, let's establish that right off the bat here. Okay, that this is going to be 3 space work. Okay, so there are three-dimensional space. Okay, so if I have 2 lines existing in 3 space, okay, these 2 lines can be parallel and distinct. We're going to use a lot of keywords here. So that they can be parallel and distinct. They can be parallel and coincident. Okay, so identical, parallel and distinct are 2 separate lines, distinct, right? Parallel and coincident are identical. Okay, we can have 2 lines that intersect. Okay, those aren't parallel or not parallel lines. And we can have a fourth case here that's a new concept called skew. And skew lines are 2 lines in 3 space that do not intersect, and they're not parallel. Okay, so we have 4 particular situations when we talk about 2 lines in 3 space, and they're right here. I'm going to leave it here for a second and strongly encourage you to get 2 pencils. Right? So try and get 2 pencils, or a pen and a pencil, or 2 straws, 2 pipe cleaners. I think we've got pipe cleaners much anymore, but if you do artwork, you might understand what a pipe cleaner is. But anyway, two lines. Okay, get 2 lines. Try and visualize 2 lines. So take a second and try then and draw, or hold the 2 pencils. Let's use pencils. Hold the 2 pencils in each of these 4 particular situations. Okay, so for the first one, we're going to have 2 pencils, and they're going to be parallel. They're going to exist. We're going to hold them out in 3 space, the space around us. They're going to be 2 separate parallel pencils. Okay. Now, second case is hold the pencils together. Okay, right on top of each other. Okay, hold them together with one hand, and that's a situation where you've got 2 identical pencils. And now I know they're not identical, but let's imagine that these 2 pencils, the one pencil would sort of just mold or fold right into the first pencil here. Okay, can we do situation number 3? 2 pencils intersecting at a point. Right, that should be easy enough to do. So hold those 2 pencils together and sort of cross them like wands or something like that, and have them intersect at a point. And then the fourth one, the new one here, the skew concept here, the skew. See if you can hold your 2 pencils so that they're not parallel, but they also would never intersect. And now think about not just the small pencil, but think about that pencil being a line that extends into infinity here. And make sure that if you do that, okay, skew situation, those lines aren't going to ever intersect. And I think with a little bit of thought, that you can show this with your two pencils. Okay, and remember those two pencils keep going on forever. They're line segments, right? Okay, or they're infinite lines. They're not line segments. They go on forever and ever and ever. So they're not parallel when they don't intersect. If you're having some trouble with it, hold one pencil, okay, directly in front of your chest, okay, and point it out, okay, out away from you, okay, so perpendicular to your chest or your body here. The other pencil you can just hold sort of at another perpendicular to that first pencil, but parallel to your body, okay, and just hold it above the pencil so that clearly they're not parallel, and clearly they won't intersect. So if you sort of have a 90-degree perpendicular angle between your two pencils, then you might have the situation where you're going to have skew pencils, okay, or skew lines. Okay, here visually, what this looks like here, intersecting a point intersecting at, okay, intersecting lines at a point, okay, and then coincident lines. Those lines are intersecting. They either intersect at a point or they're coincident. And the other situation, case 3 and case 4, is when they're not intersecting. So when they're parallel or when they're skew. And remember, notice that all of these are in 3-space situations. Okay, intersection of two lines algebraically. So when we have two lines, okay, we have, okay, parametric equations, right? Or vector equations. And we set these two lines equal to each other. And what we do when I say I set them equal to each other, I'm setting the components, right? I'm setting the x components equal to each other in both of the lines. I'm setting the y components equal to each other in both of the lines. And then I'm setting the z components of both of the lines equal to one another. Here. And then we go about solving. We're going to have situations where we've got s and t, right? S and t, s and t, s and t, and we're going to have three different lines, all in terms of s and t, that we should be able to solve for s and t. And it only takes two lines in order to solve for two unknown variables. But we have to use, okay, we get solutions for s and t that make this system work. Okay, it's solving the system. And then we check it in the third equation to see if it's satisfied. Okay, and if it is satisfied, then the lines intersect or interact in some way, and if it's not, then they don't, and we sort of go back to classifying them. So let's do examples here for each of the situation. Here's case 1, intersecting line at a point. Okay, so we've got two intersecting lines, and this situation is going to intersect at a point. This is called a unique solution in the textbook. Okay, and we get this point by, okay, substituting t into the value or s into the other value. Okay, so let's consider the two lines here. Okay, find the point of intersection of the following two lines. Show that this point is unique. Okay, so what we're going to do, okay, always is the case, is talk about L1. And I'm going to expand L1 so that I've got x equals 0 plus t, y equals 1 minus t, and z equals 2 plus 2t. Okay. L2, I can do the same. I can write x equals negative 3 plus 0s, y equals 4 plus s, and z equals negative 4 plus 2s. Okay, now I'm going to equate my variables here. So what I'm doing next is setting these two equal to each other, and setting the x components equal to each other, and then setting the y components equal to each other, okay, and then setting the z components equal to each other. So I'm going to change my pen color, and I'm going to say if x in the first line is defined by 0 plus t, and x in the next line is defined by, oh, sorry, okay, x is defined in the second line by the equation minus 3 plus 0s. Okay, can I actually solve this? Sure I can. I can get t equals negative 3. Now, that's what's nice and easy. Okay, let's take a look at the y's. 1 minus t is equal to 4 plus s. Okay, that's all right. Okay, can I work on this and solve this. Let's move the 4 over to the 1, so that'll be 1 minus 4. And I've got an s on this side. I'm going to move my negative t over here. So really I have s plus t equals 4. All right, now let's take a look at the z's. 2 plus 2t, my z component, equals negative 4 plus 2s. All right, let's do a little bit of rearranging here. I could maybe have I could move my negative 4 over here with my 2, so it'll be 2 plus 4. That allows me to have 2s minus 2t. And that'll be 6 equals 2s minus 2t. And sometimes if you like, you can divide everything by 2 to have s minus t. All right, well that's kind of interesting. Okay, so let's see. There's lots of ways we can solve this, but notice we already have t equals negative 3, and that has to be the value in order for the s components to work. So I could, literally I could start substituting in here. I could take this this t minus 3 and substitute it into my equation here. So that'd be, so s would be this would be 7. Okay. Not quite. No, I'm sorry. I better back up. Nobody, I'm sure you would have caught me in class. Okay, this is, what was I thinking here? 1 minus 4 is actually negative 3. So let's back right up here. Okay, and then I have negative 3. And clearly, okay, that would have been negative 3. That would have been, okay, s equals 0. Okay, now I have, okay, s equals 0. Okay, and t equals negative 3. And I'm going to check those in to my third equation, as I said here. Okay, so I've got left side, I'm going to go, okay, s minus t, so s minus t, 0 minus negative 3 equals 3 equals right side. And it looks like, okay, I've got a situation here where the solution to my system, okay, and it's been verified and checked in my third and my last equation, is when s equals 0 or when t equals negative 3. Okay, so now I can make a decision here. I can let t equals negative 3 or s equals 0, okay, and solve for my point of intersection here. So let's let s equals 0. So L2 is the line we're going to use, and our point, okay, in L2 is going to be, okay, the point x, y, z, and that equals negative 3, 4, and negative 4, plus 0 is my s value, times 0, 1, and 2. Okay, so our point of intersection, okay, is going to be nothing over here. Okay, and that's my point of intersection here. So that's where the two lines intersect. Now, I could have gotten that same point if I would have chose t to be negative 3 here. So I would have had 0 minus 3, okay, 1 plus 3, and 2 take away 6, right? And that would have been the point negative 3, 4, and negative 4. Okay, that's really how we do things, okay? We look, okay, we expand our vector equations to parametric equations. We equate our exponents. We write the parametric equations out and we equate exponents. We try and solve for the system, and if the solution can be solved, then okay, we move forward and think that these lines are, okay, going to intersect. Okay, how about the situation where we've got coincident lines? Okay, coincident lines are lines that are identical, they're the same. Okay, Now in this case, we've got an infinite number of solutions. Okay, we've got two identical lines, and when they lie on one another, there's a whole bunch of infinite number of solutions here. Okay? And we talk about the term here being parallel and coincident. Okay, so for an infinite number of planes. So here's the situation for this one. Okay, we've got two lines. Okay, okay. We're going to look at these. We're going to solve these the same way. I'm going to let in line 1, I'm going to let x equal, that'd be 0t, y equal negative t, and z equal 2t. I don't have any point here. Okay, so there's no point, 0. It's just a parameter equation. L2 gives us x equals 0 plus 0s, y equals negative 6 plus 3s, and z equals 12 minus 6s. All right, now I equate exponents. I'm going to do this over here. I'll do it down here. So I've got 0t equals 0 plus 0s, and that's my x component right here. Well, that's really silly. That really doesn't give us anything here. There's no solution here, okay? Well, or is there? Okay, is there multiple solutions? There's not no solution here. Okay, there's an infinite number of solutions because t okay, so there's an infinite number of solutions. I'm going to spend a second and talk about this. Okay, because t really can be anything, right? And s can be anything. Okay? Because the equation 0t equals 0 plus 0s, if I put any value for t in here, times 0 is going to give me 0. Okay, so when I have this situation, okay, t can be any value or s can be any value. That leads to the fact that it's an infinite solution. All right, well, let's go to y. Let's look at y's here. Negative t equals negative 6 plus 3s. All right, well, that would give us 6 equals 3s plus t. Okay, that's fine. How about my z components? 2t equals 12 minus 6t. Oh, s, I'm sorry, s. Day starting with mistakes here. Silly mistakes. That's s. Okay, and then that will be s as well, too. If that makes more sense now. Okay, so let's quickly solve this. So that'll be 6s minus 2t equals 12. Okay, now let's look at my two equations here. 6 equals 3s plus t, and 12 equals 6s plus 2t. And I want you to stop there and notice something, okay? Now if I go and try and solve these are identical, right? Those are identical lines, okay? And I don't have, okay, a solution here, and it's basically the same situation here. I've got infinite solutions here. Okay? When I have identical lines, I've got an infinite solution here. So the infinite idea turns up lots of times here. Okay, so when we set up our system and we can't solve, okay, we've got an infinite number of solutions here. So we try and work this out, okay, but we just can't solve it. We don't have enough information in our lines because the lines are identical. Okay, and I need two separate or distinct equations in order to solve. Now, before we finish this example, I want to go back and take a look at the original question here, okay, and look at the direction vectors here. Okay, our direction vectors, okay, suggest that these two lines, okay, are parallel. And look at our direction vectors. Our direction vectors are combinations of one another. If I take, okay, D1, if I take D1 and multiply it by -3, I get D2. Okay, so these are parallel. So I've got a situation where, okay, I've got parallel lines. Now, this particular situation, they might be parallel and coincident, or they might be parallel and distinct. So if I go about solving it this way, okay, then I just have to check my point and see if it's in the other line. And if the point is in the other line, then they're parallel and coincident, right? They share a common point. But if it's not in the line, I know they're parallel and distinct then. Okay, moving on. Okay, the third case is parallel lines. The two lines are parallel. They'll be separate lines, okay, so they'll be parallel and distinct. In this case, there's going to be no solution. So this happens when we try and solve a system, we get at least one false statement, like the statement 0 equals 1. Okay, then the solution clearly has no solution, or the system has no solution, and the lines don't intersect. Okay, they're parallel, but they don't intersect. Now, by way of cross product, okay, some students work on this. In addition, the lines are parallel. If the cross product is equal to 0, the cross product of the two direction vectors is equal to 0, then the lines are parallel and distinct. So let's consider this example. Find the point of intersection between the following lines. Now, right off the bat, before we dig into this, I want you to look at the direction vectors here. And clearly the direction vectors are connected. Okay, now what's my relationship for my direction vectors here? So D1, if I multiply it by -2, I get D2. Okay, so these are parallel. These are absolutely parallel lines. Okay, that's fine. So now we've narrowed our 4 cases down to 2 cases. Okay, so I'm under the impression here, basically by simply by looking at and understanding a little bit about direction vectors, okay, I know, okay, that I've got this particular situation. So if they're parallel and coincident, like the last example, we'll get a situation where we've got equations that we really can't solve. Okay, so let's set this up. I'm going to change my pen color, okay, to be consistent with. So for line 1, I've got x equals -2 plus t. I've got y equals 3 minus 2t. And I've got z equals 1 plus t. For line 2, I've got x equals 0 minus 2s. I've got y equals 2 plus 4s. And I've got z equals 1 minus 2s. Okay, let's quickly equate components here. -2 plus t equals 0 minus 2s. I'm going to just rearrange. T plus 2s equals 2. Now my y's, 3 minus 2t equals 2 plus 4s. Okay, I can juggle this around. 3 minus 2 is 4s plus 2t, okay, or 4s plus 2t equals 1. I think this one in here is okay. I've got okay, either way, I'm just checking, I'm just verifying. Okay, that's got this different in my notes here. I'm just checking my x component here. I think I did that all right. Yeah, okay. And then let's do my z component. 1 plus t equals 1 minus 2s. And that'll be t plus 2s equals 0. Okay, so let's try and, okay, let's deal with, let's call this equation 1, this equation 2, and this equation 3. All right, so let's try and, okay, look at my s's here. Let's take equation 1 and equation 3. And equation 3 is t plus 2s equals 0. Now if I subtract these equations, I'm going to have 0t plus 0s equals 2. Okay? And okay, that is not something I can solve here. There's no way, if I multiply my two variables each by 0, there's no way I'm going to get 2. Okay, so that's an inconsistent system, right? Okay, and there's clearly no solution in this case. So we knew they were parallel, okay, and we found that there's no solution that solves this whole system here. So I can conclude, okay, that the lines are parallel and distinct. Right here, when I get an equation, okay, that crumbles, falls apart here, I can't solve this. Okay, I didn't even have to use my second equation, but in fact, if I did, I would have gotten the same situation. Notice the coefficients, and I think that's going to be the giveaway mark here. Okay, so t, okay, 1 and 2, okay, 2 and 4. Okay, there's always a ratio here of 1 and 2, okay, or 2 and 4, and that same ratio is 1 and 2. So when those ratios are the same, and we've got different values here that don't follow that same ratio, then clearly we're not going to be able to solve this system. And this is what we've got here, okay, parallel and distinct. All right, finally, skew lines. Okay, skew lines, okay, can work or develop when we're solving a system and we get at least one false statement. Okay, we should look at, okay, the fact that the cross product won't equal 0, okay, and they have no point of intersection here. So right off the bat, okay, look at our direction vectors. Okay, they're not related at all. Okay, okay, so these are not parallel lines. Okay, that's fine. Okay, so let's try and work on our equation. I like to consider doing these always by writing my x component, okay, for my line 1, and that's 1 plus 0t, y would equal negative 1 plus 0t, and z equals 0 plus t, and L2, okay, will be negative 2 plus s, y equals 1 plus 0s, and z equals 0 plus 0s. Okay, there's a lot of zeros in here. Okay, well, that's fine. Let's equate exponents. Okay, so x is going to be 1 equals, I'm going to drop the 0t, negative 2 plus s. I can solve for s right off the bat here. That'll be s equals 3. Okay, y gives us negative 1 equals 1, which is not true. Okay, so we can't really go anywhere. There's no solution for that. And z gives us t equals 0. Okay, well, this little situation right here, this is not a true system. It's a false statement. Negative 1 equals 1. We need consistent solutions. We need everything to sort of work out nicely. So now we've got this situation where they're not parallel, okay, and they no intersection. Okay, so therefore these are skew lines. Okay, that's 4 examples, 4 different situations here. Okay, that's going to allow us to deal with the way 2 lines interact with each other. Classification of using vectors. Okay, I'm going to just leave this up here. Okay, if you'd like to just jump in and do cross products, I'm not sure anyone does. Okay, but we can talk about, okay, if the cross products are 0, they're parallel lines, and if the cross products aren't 0, they're non-parallel. And I can further do another classification step here to narrow these cases down. I don't mind using this solution method, or okay, there's this classification method. Okay, but I kind of just like to prefer to start solving the systems. I'm going to do one more example, and I'm just going to leave it here, pause for a second, okay, and get on to, okay, probably doing this in Smart Notebook. Okay, the last example for 9.1, with this video, we're going to do a second video for lines intersecting with planes. Requires you to use the vector method presented above to classify each pair. And we're going to just look at direction vectors here and okay, try and do this really quickly here to classify whether they're parallel and distinct, parallel and coincident, not parallel and intersecting, or not parallel and skew lines. Okay, first one here. Look at the direction vectors here. I've got a direction vector 1, 2, 3, and I've got a direction vector here of this line, -2, okay, -4, -6, and they're connected by the factor -2 here. Okay, so I know these lines are parallel. Okay, so I'm going to then take a look at how I can check then the point. I'm going to choose this point and see if it lies on my other line here. Okay, so I've got -2 equals 0 plus t. Okay? And I've got -1 equals 1 plus 2t. And I've got 0 equals 2 plus 3t. Now, in this case, t equals -2. In this case, I've got, -2 equals 2t, or t equals -1. And right off the bat, I don't have a consistent solution. T, doesn't consistently give you the same value. Okay, so if I can't show that one of the points on one of my lines lies on the other line, I can conclude that these are parallel and distinct. Okay, and it's really that simple. Okay, let's look at B. Okay, again, look at the direction vectors first. Okay, and now it looks like my direction vectors in this case is if I multiply 3 times D1, I get D2, right? Okay, so let's take a look at my point and see if it lies on. Okay, so yeah, sorry, so this was parallel. Okay, I know they're parallel when I can connect the direction vectors. Now I'm going to check my point on my other line here. Okay, this is going to be an easy solution to solve here. Okay, is there a common value of t? Okay, where -4 equals t, 4 equals -t, and 0 equals 0t. Yeah, clearly right there. Okay, if I let t equals -4, okay, I get a consistent solution. So I know that they're parallel and coincident, right? Okay, and that also leads to coincident, right? Because t can be anything in here. All right, next up, C. Look at my direction. Okay, look at my direction vectors here. D1 is not a combination of D2 in any way. Okay, so these are not parallel. All right, so then I go and try and let's do the cross product thing if they're not parallel. Okay, I can clearly show that my two direction vectors do not equal 0. Okay, so they're intersecting or they're skew, and I think if I connect them in C, okay, so if I connect 2 plus 0t equals 0 plus s, okay, or 1, okay, my y components here, 1 plus t equal 1 plus 0s, okay, and then my z components, 3 plus 2t equals -1 plus 2s. See if I can solve these. Okay, so here I've got s equals 2. Okay, here I've got 1 plus t equals 1. here t equals 0. Okay, and does that work with this one? Let's rearrange this one first here. So I'm going to have 4 equals 2s minus 2t. Okay, or 2 equals s minus t. And do I have a left side here, okay, equals 2, and a right side is s minus t, and I know s to be 2, and I know t to be 0, so that does work, and these must be, okay, intersecting, parallel, not parallel, and intersecting. Okay, every system works at, let's say it's intersecting at t equals 0 here, so at t equals 0, okay, that's going to be this line here, so they're intersecting at, okay, when t equals 0, this whole direction vector is negligible, right? And it's intersecting at 2, 1, and 3. Okay, and finally, okay, the next one here, okay, start with your direction vectors. Clearly d1, okay, is not equal to a scalar multiple of d2, okay, so they're not parallel. Okay, let's try and set up my equation here. I bet you these ones are skew, but we're going to check our components here. So in the first line, I've got my x component 1 equals s. Okay, my second line. Then I've got my 0 equals 1. And then I've got my z component 0 plus t. So 0 plus t equals 0. Okay, so t must equal 0. This is no solution. Okay, and what do we know when s equals 1, but there's no solution for this one? T equals 0. These are skew lines here. Okay, and that's legit math. There's not a lot of math here, but if we know our two terms, we know our two, okay, if we know our two, or sorry, our 4 concepts here, okay, we can try and solve this and work with this, okay, where we've got these situations here. Okay, so that's a long video, and there's even going to be a second part to this. It won't be near as long, okay, but certainly talk about situations when we've got two lines working together in 3 space. So good luck with some of these homework questions, and we'll get continuing to work on this.